So the expression was HA and acid was dissociating to produce H plus 1 and A minus 1 ions, right? And taking the equilibrium constant of this was called the dissociation constant, product concentration, divided by the reactant concentration. So divide by the reactant concentration, which is the acid in this case. And you had this expression, and this expression was further changed into K was equal to H plus 1 squared, because divide by the acid concentration. So it was further written as this, because these two ions would be produced in the same quantity if it's a weak acid. If it's a buffer solution, then you add this A negative ion, the conjugate base extra, by adding a salt. So the formula would change. So for a pure weak acid, only, you had this expression, and for a buffer solution, where you want the equilibrium to move forward and backward, so you add extra A negative ions. The expression becomes the salt concentration or the conjugate base concentration into H plus 1 divided by the acid concentration. Right? So this was the formula for a buffer. Sarah, so far, this is clear. We're done with this, right? Is this all clear?
Yes. Yes, sir.
The only thing I wanted to tell was, add was that, and we did explain this earlier, Ka higher means more dissociation. It means the acid, the products are, you have more products. You have more H plus 1 and you have more A minus 1 ions. So Ka higher means more dissociation, and it refers to a stronger acid. But if the same expression, if you take the negative log of Ka, you get pKa. And pK for strong acid, pKa, the negative log, whenever you take negative log of something, H plus 1, you get pH. Negative log of Ka would be called pKa. Whenever you take negative log, if Ka is higher, then pKa would actually come out to be lower. pKa would be lower. You can even check this, that just hold on 1 second.
शॉर्ट मैंने भी दिया था
Wait, as a negative log of K is equal to pK. Now pK would be low. You can even have like, for example, if pK is 1 into 10 to the minus 4, if K is 1 into 10 to the minus 4, and you take the negative log of this, you get a value which is 4. Right? So if K value is 1 times 10 to the power minus 7, 1 times 10 to the power minus 7, you take the negative log of this on your calculator, you get a value of 7. So you can even confirm this, that if the value is lower, 1 into 10 to the power minus 7 is a smaller value. It's a smaller value. 10 to the power minus 7 is a smaller value. So if you take the negative log, you get actually a bigger value. pK would come out to be bigger. Sarah, is this clear?
Yes, sir. Sir, you mean like if the acid is the higher, no, like the pH will be lower, like 2, 3.
I mean, whenever you take the negative log of something, like P stands for negative log, right? Like if there's more H plus 1, what does that mean? It's a stronger acid. That means pH would be lesser. Right? For example, if H plus 1 concentration is 0.1 mole per dm cube, and you take the negative log of this thing and you try to calculate pH, the pH would come out to be equal to 1. So it's going to come out to be a smaller value. If H plus 1 concentration is really, really low, like 0.0001 mole per dm cube, on your calculator, you take the negative log and you try to find pH. The value comes out to be actually, for this, it's probably going to come out to be 6. So my only point is that whenever you take the negative log of anything, a smaller value actually turns into a bigger value, and a bigger value turns into a smaller value. H plus 1 higher means pH would be lesser. H plus 1 lower would actually mean pH is higher. So is this point clear?
Yes, sir.
I mean, the same is true for Ka. Like I told you, now I'm going to repeat everything and recap everything. The same would apply to Ka. Ka higher means, so Ka higher means that you have more dissociation. Like more products would be formed, so the numerator would be bigger. There would be more H plus 1 and A minus 1 ions because there's more dissociation happening. That's the reason why Ka would be higher. And there would be less Ha and there would be more H plus 1 and A minus 1 ions. So Ka higher means more dissociation, that means stronger acid. But if Ka is higher and you take the pKa, you take the negative log of this, the pKa would actually come out to be lower. So is this point clear?
Yes, sir.
So just remember, for strong acids, the Ka would be higher, or vice versa, the pKa would be lower. So we're going to try and do some questions. So we're going to try and do some questions now related to dissociation constant Ka. Let me just check if I've opened those questions. We're going to try and do some questions. We have, right. We can start with this one. Although this is part of organic, we can even we can skip the organic part. I mean, this part we can skip for now. So let's ignore this for a second. Now the question is the medical value of Ka for methanoic acid. So they've given Ka over here. Now the methanoic acid is given, and this is for, which acid is this? This is pyruvic acid. So some acid, both have carboxylic acid functional groups in them. Which one is a stronger acid? This one is a stronger acid. Okay, I don't think they've even asked for that, but it has a higher Ka value. So there's a higher Ka value, so it's going to be a stronger acid. Now, an equilibrium mixture containing the two acid-base pairs is formed. Use the Ka value to calculate the equilibrium constant for this particular equilibrium. Now this is a tricky question because they're not asking you to calculate Ka. They're actually asking you. The first question that we're doing is a tricky question. They're actually asking you to calculate the equilibrium for this reaction, for this particular reaction, K equilibrium. So what is the equilibrium constant, K equilibrium, for this reaction? It's products over reactants, right? These are your products. So these over here are my products, and these over here are my reactants. So it's products concentration divided by reactant concentration. So it's going to be HCO2H, methanoic acid concentration. That's my product. The other one is CH3. The other one is CH3CO, CO2 minus 1. CH3CO and CO2 minus 1 concentration, right? And you divide the whole thing by the reactants, which are HCO2 minus 1 concentration and CH3 CO2 H concentration, right? This is the expression, but they're not asking for the expression. Is this expression clear? Abdullah, is this clear? Mehfooz? Sir, is this clear?
Yes, sir. Do we also include the units?
No, we're going to include, I mean, they haven't asked for the units. We're going to include, I mean, they're not going to be any units. Like concentration into concentration divided by concentration into concentration, it's going to get cancelled out. So we don't have any units so far. But how do we get the value of this expression? That's the big question. So what we're going to do is, I mean, no information is provided except that you're given Ka values for methanoic acid. Now, now you're given Ka values for methanoic acid. Now, methanoic acid has, I mean, Ka is for dissociation. So the Ka value is given for this reaction. Like methanoic acid is an acid, it dissociates and produces two ions. One is H plus one, the other one is HCO2 minus one ion, right? The carboxylic acid H plus one is lost. So the Ka value, I mean, I'm going to rub this. So the Ka value is products over reactants for an acid dissociating, right? It's an acid that dissociates to produce H plus one and A minus one ions. So in this case, it's H plus one concentration into HCO2 minus one concentration and divide the whole thing by the acid concentration, which is HCO2 H concentration. Now I know the value of this expression. This expression, the value is given over here. It's given as 1.78 times 10 to the power minus 4, right? So is this clear?
No, I don't understand how the HCO2 the equation is.
Need this one?
Yes, no, like why we changed it? We just add the ions.
Nini, what did I say Ka was? Ka was the dissociation constant of an acid, like any acid. It breaks down and produces H plus 1 and some other ion. So all acids can be represented by this equation, right? So in our case, we have methanoic acid. They've given us the value of Ka. Ka represents the dissociation constant. Methanoic acid is this thing, C double bond O and OH. Like they've given us HCO2H, right? Like carboxylic acids in AS. What do carboxylic acids do? How do they behave as acids? The H plus one at the end, this H plus one over here, it breaks down, dissociates, and ionizes and produces these two ions. Like this H plus one over here, it's going to break down and it's going to produce H plus one ions. Plus what's left would be HC double bond O and O minus one ions. Sorry, do you get this part?
Yes, sir. Thank you.
I said, but remember, Ka would represent, whenever they talk about Ka, it would represent the reaction, it would represent the equilibrium constant for a reaction where an acid is dissociating. So if we go back to our question, they've given us, I mean, ignore all of this. They've given us methanoic acid, they've given us the Ka value. So I wrote down methanoic acid, I wrote down that it's going to dissociate like any acid. And the equilibrium constant of that particular reaction is going to be called the Ka value. It would be H plus 1 concentration into A minus 1 concentration divided by the acid concentration, which is over here. And this value is given as 1.78 times 10 to the power minus 4 over here. Right? Is this part clear?
Yes.
Now, the other one. The other one is also a similar acid. It's CH3CO CO2H. So it's CH3 CO and CO2H. And it's also going to dissociate and ionize. It's going to produce CH3 CO and CO2 minus 1 ions and H plus 1 ions. Right? The H at the end is going to, it's going to dissociate. So the H at the end is going to dissociate. And if I write the Ka expression, in this case, it's going to be product concentration, like CH3CO, CO2 minus 1 concentration into H plus 1 concentration. Divide that by the acid concentration, which is CH3, CO, CO2H. And the value is provided. It's provided over here. It's given as 4.07 times 10 power minus what? Minus 3. Right, Sarah? Is this clear? These two expressions.
Yes, sir.
Achha, so the thing is, we have Ka for one acid and we have the Ka value of this other acid. But they had asked us to calculate the equilibrium constant for this particular reaction. I mean, they've just they didn't tell us to use Ka. They just told us that find the equilibrium constant for this particular reaction, product concentration divided by the reactant concentration. Now, this is the expression that we need to find the K value for. The only problem is that we don't have any information about this reaction. But what you can actually see is, if you look carefully, you can combine the K expression of this with the K expression of this. I mean, let's call this Ka1 and let's call this Ka2. Like, both expressions can be combined to give you this expression. I mean, you have to observe carefully. Like, if I multiply uh, Ka2 with 1 over Ka1, if I do that, I'm going to get exactly I'm going to get exactly the same expression. Okay, I'm going to try and do this. So I'm going to multiply Ka2 with not multiply, actually. I'm actually dividing Ka2 with divide by Ka1. So what is Ka2? Ka2, this one over here. That's CH3, CO, and then there's CO2 minus 1 on the top. Concentration into H plus 1 concentration divided by the CH3CO, CO2H concentration. I mean, this value, I have this value. I have the value. It's 4.07 times 10 power minus 3. And I multiply it by 1 over K1. K1 is this thing. Now, 1 over K1 would be, the whole thing would be flipped around. So let's use a different color. This thing, the HCO2H would be on top. So get the HCO2 H on top, divide that by the H plus 1 concentration into HCO2 minus 1 concentration. And I'm multiplying the two expressions. This is Ka2 multiplied by 1 over Ka1. Now, what do you think is going to happen? Like, if you simplify the expression, the H plus 1 would get cancelled out. And the expression that you have left now is exactly this expression over here. So, do you get this part?
We combine both of them.
Yes, I mean, they had asked us to calculate the equilibrium constant for this reaction, right? The one that I'm pointing to. And we figured out that the equilibrium constant would be the product concentration divided by the reactant concentration. Is this part clear, Sarah? The first part.
Yes, sir.
Achha, and then they had asked us to calculate the value of this equilibrium constant, this red one. Now we had no idea where to get these values, right? I mean, they didn't give us any values of anything. What they gave us was they gave us the K value for HCO2H. So I wrote down the K expression of HCO2H, products divided by reactants, an acid dissociating, and I had this value. And I had Ka for this other acid, pyruvic acid. And I wrote its dissociation and I wrote the expression for that. And I had the value for this expression. And what I saw was that if I combine the two expressions in a particular way, I will get this expression over here. This is the expression that whose value we were trying to calculate. So I have figured out that if I multiply Ka2, which is this thing, with 1 over Ka1, so that's what I did. I multiplied the expression for Ka2 with 1 over Ka1, which is this expression over here, but upside down because it's 1 over Ka1. the H+1 concentration would get cancelled out, and the expression that I had left after doing all of that was exactly the same expression that I was looking for. So, do you get this part?
Yes, sir.
I mean, this is a tricky question. This is a very tricky question. So, you had to figure out that a combination of Ka1 and Ka2 would lead to the same expression, whose answer that you're looking for. So that means I just need to multiply Ka2 with 1 over Ka1. I have the value of Ka2, so I'm going to do this now. I have the value of Ka2. I mean, Ka2 was which one? It was this one. It's 4.07 times 10 to the power minus 3 multiplied by 1 divided by Ka1, which is this expression over here, methanoic acid. It's 1.78 times 10 to the power minus 4. So is this clear?
Yes, sir.
Tell me what the answer is. Mehfooz, if your mic isn't working, try and send it in the chat.
Is the answer 22.9?
Okay, so the answer is coming out to be 22. Yes, I think it would be 22.9. So probably going to be 22.9, right? So this one was a tricky question. Now the next one is use your K equilibrium to predict the position of this equilibrium by placing a tick, whether it's in the middle or to the right or to the left. So remember that any equilibrium, it's basically a ratio of the product concentration divided by the reactant concentration, right? Any equilibrium, even if you're talking about Ka, it's product concentration divided by reactant concentration. But this time we're talking about this equilibrium over here. Now, any equilibrium constant is product over reactant. So if you have more products, the value is going to be greater than 1. So if you have more product concentration compared to reactant concentration, the K equilibrium would be greater than 1. If you have more reactant concentration compared to product concentration, the K equilibrium value would be lesser than 1. So do you get this part? Like if you have more products, then obviously, and you have less reactants. Like if this equilibrium, is this part clear?
Yes, sir.
So if you have more products, then obviously at equilibrium, that means the reaction is favoring the forward reaction. Then obviously K equilibrium would be greater than 1, and if the backward reaction is being favored and you have more reactants, then obviously K equilibrium would be less than 1. So your K equilibrium is coming out to be greater than 1. So that means it's going to favor the products. It's going to be to the right. Is that clear, Sarah?
Yes, sir.
So then the next part is, let's move to the next question. Now the question is, this ethane dioic acid, and it has two dissociation constants, K1 and Ka2, and you're supposed to suggest equations to show the two dissociations giving rise to these pK values. So I'm going to explain this over here. As I remember, hopefully you know how carboxylic acids work. Like all carboxylic acids, this serial bond O and OH, they're going to ionize and they're going to produce O minus one ions and H plus one ions. Now, one thing I told you early on, which was that when an acid dissociates, and when we talk about equilibrium constant, this Ka value, it's only for one H plus one that's dissociating. Like if you have a triprotic acid like H3PO4, So I had explained earlier. Now H3PO4 is capable of producing three H plus ions, right? Like if it fully ionizes, it's going to produce three H plus ions and one PO4 3 minus ion. But the thing is that this H3PO4 is not going to dissociate in one go, and you're not going to treat it as one single acid. This is the structure of phosphoric acid, which is P double bond O, and then there are three OH groups attached to it that release H plus ions. Now the thing is that these H plus ions, they don't all lose their H plus one in one go. The first thing that happens is that one of the H plus one it actually decides to break away. So that's dissociation number one. So it's going to dissociate stepwise. Like if you have a diprotic or a diprotic or a triprotic acid is one which has more than one H plus one ions, or it's capable of releasing more than one H plus one ions. So it's going to produce an H plus one ion and it's going to produce an H2 PO4 minus one ion, right? I mean, it's HA, an acid, dissociating to produce H plus one ions and any other random ion, A minus one ion. So that's dissociation number one. And this would be called dissociation constant number one. Like if you calculate this, it's going to be H plus one concentration multiplied by H2PO4 minus one concentration, and you divide the whole thing by H3PO4 concentration. So this is called Ka1. That's phosphoric acid dissociating for the first time. Right, Sarah, is this part clear?
Yes, sir.
I said, then you have the second dissociation. The second dissociation is that this H plus 1 has already dissociated, so it's gone. What you have left is this molecule now. Now, another H plus 1 is going to break away and it's going to dissociate. So, your starting point now is H2PO4 minus 1. Like one of the H plus 1 was already gone. I mean, you left with this thing. I'm going to highlight the equations. This is the first dissociation equation. The first H plus 1 is already gone. Now you're breaking off the second H plus 1 ion. So it's going to produce an H plus 1 ion, and what's left would be HPO4 minus 2 ion. And you can, let me highlight this. This is the second dissociation. And this would be called Ka2. I mean, if you calculate the equilibrium constant or dissociation constant of this, it's going to be referred to as Ka2, which would be H plus 1 concentration multiplied by HPO4 minus 2 concentration. And you're going to divide the whole thing by H2PO4 minus 1 concentration. Uh, and then obviously you're going to have a third dissociation, that the third H plus 1 is going to dissociate. So the third dissociation would be that you're left with HPO4 minus 2. And it's going to dissociate and it's going to produce another H plus 1 and PO4 minus 3. So the last H plus 1 has broken off. And the last Ka expression would be Ka3. The third dissociation would be that it would be H plus 1 concentration. So every time your Ka expression is exactly the same. I mean, it's the same standard format that it's following. Divided the whole thing by HPO4 minus 2 concentration. So three separate dissociations, three separate reactions are happening. You're not going to treat phosphoric acid as one acid. It's actually a combination of three acids. The first one was H3PO4, that dissociated. Then you had H2PO4, that dissociated, and then you had H2PO4 minus 2 ion, which is going to dissociate the last. So is this part clear?
Yes, sir.
Which one do you think is the strongest of the three? Like,
Is it the the first dissociation? The first one?
exactly, because after that, the ion becomes negatively charged. And after the second dissociation, it becomes even more negatively charged. So instead of actually losing H plus 1, it would start attracting H plus 1. So first dissociation is the easiest. Remember that. So first dissociation is easiest. After which ion becomes negative and instead would start to attract H plus 1 ions. So it would start to attract. Okay, is this idea clear?
Yes, sir.
So the first K would be higher. Like I can write an expression over here. So first Ka is going to be higher. So it's going to be K1 would be the greatest value. Then it's going to be higher than Ka2, and Ka2 would be higher than Ka3, the third dissociation. So after the first dissociation, usually all acids they become really, really weak acids. And in terms of pK, if you use pK, what did I tell you? A higher pK, a higher Ka value would result in a lower pK value. Like if you take the negative log, everything would switch. The higher value would become the smaller value would become the higher value. Now, anyways, we're going to try and so we're going to try and where were we? Just one second. Now, now this one. Coming back to our acid, the question that we were doing, they had started talking about this acid, ethane dioic acid. Now, ethane dioic acid, if I draw the acid over here, uh, but there's not enough space, let me draw the acid over there as well. So let's talk about ethane dioic acid. What's what's going to happen with ethane dioic acid is that it's also a diprotic acid, which means that it has two H plus 1 ions. I mean, this is the formula that's given. It's going to have a carboxylic acid group on one side, and it's also going to have a carboxylic acid group on the other side. So on both sides, you have a carboxylic acid functional group. I mean, this is how they had written it, like COOH, and on the other side there was C double bond O and OH. Now, it is capable of losing two H plus 1 ions. One H would be lost from here, one H would be lost from here, but it's not going to do that in one step. What it would do is it's going to first dissociate. Uh, one of the H's would be intact, the other H plus 1 would break away. And in the next step, the H on the left has already broken away. Now the H on the right has already broken away. Now the H on the left would break away. So sorry, is this clear?
Yes, sir.
So these are the two dissociations of this ethane dioic acid, and the first one would have a higher Ka value. So it's going to have higher Ka value, or if we talk about, and the next one would have a lower Ka value. It's not going to dissociate that much because it's a negative ion. Negative ions don't lose H plus 1 ions; they actually attract H plus 1. So it would be much more difficult for it to lose an H plus 1 ion. I say anyway. So you have these two Ka values. And if you talk about pK values, then pK value for the first one would be actually a higher K value indicates that the pK value would be lower. And for this, the pK value would be, it's going to be higher. So these are the two dissociations that you had to write over here. So this is the first dissociation, the lower pK value, and this is the second dissociation, the higher pK value. So you have to write these expressions over there. So is this part clear?
Yes, sir.
Then just hold on 1 minute. We can just finish this question quickly. That they're asking in part 4. They're asking the pK value, the relationship between K and pK. You're just going to state that pK is basically taking the,
Negative log Ka.
yeah, exactly. That's it. That's the answer.
Okay.
1 mark. This one is organic. Forget this one. And this one they're asking to write the expression for Kw for D2O. Remember, what was Kw? Kw was the dissociation constant of water, right? Like water ionizes and produces two ions. One is H plus one, the other one is OH minus one, right? And water was had a concentration of 1 into 10 to the minus 7 pure water, mole per dm cube. This as well, mole per dm cube. Now the thing was that Kw was the ionic product of water, H plus 1 concentration multiplied by OH minus 1 concentration. And it had a particular value because it was 1 into 10 to the minus 7, the concentration multiplied by 1 times 10 to the minus 7. The value came out to be 1 times 10 to the minus 14. And we took the negative log of this, and then it gave us pH plus pOH is equal to 14. Right? Sorry, is this clear? Hello, Sarah, is this part clear?
Yes, sir.
I said so, but the only thing is that they are asking for D2O. D is, remember, is an isotope of H. Hydrogen has an isotope which is D. Like it has one more neutron. So you write the same expression. It's going to be D2O. It's called deuterium. And it's going to produce D plus ions and OD minus 1 ions. Like D is H. So it's just the same expression. You just have to write the expression D plus 1 ions into OD minus 1 ions. That's it. Right? Is that clear? And this is known as heavy water. And over here, so is this clear? Yes or no?
Yes, sir.
So it's exactly the same expression, except H is written as D. And calculate the pH of pure neutral D2O at 298 Kelvin. Assume that D plus 1 is equivalent to H plus 1 for pH calculation. So they're saying that D plus 1 and H plus 1 are pretty much the same thing. Now, the Kw value is different for this heavy water, deuterium. So you're going to write that, I mean, when water ionizes, it produces the same amount of both ions. If D2O ionizes, it's going to produce the same amount of both ions. So that means Kw could be written as D plus 1 squared, right? Because these two values are, I mean, if D2O is ionizing, it's going to produce the equal amounts of both ions. So it's going to be D plus 1, whatever that value is, the same would be the value for OD minus 1. So you can write it as D plus 1 squared. You have the Kw value, it's 1.35 times 10 per minus 15. And you can find the concentration of D plus 1 ions. Once you find the D plus 1 ion concentration, you can take the minus log of D plus 1 concentration, which is minus log of H plus 1. And you can find the value of pH. Is this clear, Sarah?
Yes, sir.
Okay, so we're going to continue with this worksheet tomorrow then. Try and go through these questions again. I'm going to send this worksheet in the WhatsApp group as well.
Okay, thank you, sir.
Okay, take care. Allah Hafiz.
Allah